Topic 2, Part A, Graphing Quadratics. We're going to focus this entire topic on quadratic functions. There are different forms for graphing a quadratic, and we'll start with vertex form. We'll identify key features and write equations. From topic 1, a quadratic function is a function of the form f of x equals x squared. It's a non-linear function, and the parent function has a vertex at 0, 0. On the right, it says describe the transformations to the parent function f of x equals x squared. Then graph the function. Well, we know this is our parent function, so let's look at describing what's happening with h of x. H of x equals 2 times x minus 1 squared minus 3. So this is so far all review. That 2 does something, the x minus 1 does something, and the negative 3. Let's see what we can remember. That 2 on the outside, since it's greater than 1, will stretch vertically by a factor of 2. So we would say stretches vertically. The x minus 1 on the inside actually moves the entire function 1 unit to the right. So we'd say moves right 1. And then that minus 3 at the end moves everything down 3. Did that sound familiar? I hope so. Now let's take a look at sketching the graph. If we start with our parent function, we know the vertex is 0, 0. Let's go ahead and plot that point. And then if I go 1 to the right or 1 to the left, 1 squared is 1, and so is negative 1 squared. We'll plot those points. Keep going. 2 squared would be 4, and negative 2 squared is also 4. Oops, I didn't go up too far, or far enough, I should say. We'll get that point in the right spot. So 2, 4, and negative 2, 4. There we go. And if we keep going, that looks like it's a little off, doesn't it? I think it should be good, though. If we keep going to 3 and negative 3, whoops, there we go. That should put us to the top of our graph. 3 squared is 9, and so is negative 3 squared. So on the right, and then over here on the left. Go ahead and pause the video and draw a curve through those points. And there's the graph for our quadratic parent function. Now let's take a look at how we can create a table with our x's and our y's. We know that anything moving left or right, or stretching or compressing horizontally, affects x. So our original value is just plain x. Since we're moving 1 to the right, we're actually going to add 1 to all of our x values. So let's do that first. Take everything in this column and add 1. We'd have 0 plus 1, 1 plus 1, negative 1 plus 1, 2 plus 1, negative 2 plus 1, 3 plus 1, and, whoops, here we go, negative 3 plus 1. On the right, we have our y values. Well, I'm not going to have enough space for that, am I? So I'm going to move that star over just a little bit. There we go. Normally our y values are just plain y, but now it moves, or it stretches vertically by a factor of 2, so we're going to multiply all the y's by 2, and then since it moves down 3, we'll subtract. So now, do you guys remember doing this before? This was kind of tricky. Now we're going to take all of our y values, multiply them by 2, and subtract 3. Let's see what that'll look like. 2 times 0 is 0 minus 3. 1 times 2 is 2 minus 3. 1 times 2 is 2 minus 3. We got a bonus on that one. The next y value is 4. 4 times 2 is 8 minus 3 is 5. And then 4 again, so 5 again. Last but not least, ooh, these are kind of off our graph, aren't they? 9 times 2 is 18 minus 3 would be 15. So that's too far off of our graph. We'll stick with the points that we see. All right, go ahead and plot these points. 1, negative 3, 2, negative 1, and 0, negative 1. Let's see, 3, 5, that's way up there. There we go. And negative 1, 5. See if you can connect these sets of dots and go all the way to the top of your graph. Can you see that the shape of that graph is stretched vertically? It's not as wide as the original one, it's more narrow looking. We also moved it 1 to the right and down 3. Now that seems to work for sketching the graph of a transformation, but there's got to be a better way. First, let's take a look at the name of our graph. You see that word on the right, parabola. The parabola is the name of the graph for the quadratic function. So we would say, so the name of the graph. That's actually its shape. So the shape of a graph is called a parabola. When we have these transformations, it's actually a certain type of form, and that form is called vertex form. Vertex form is a quadratic function, but it includes all the components of a transformation. We'll set it up as y equals a times x minus h squared plus k. The a, h, and k values would all be numbers, like we see up above in that equation for h of x. Using the a, h, and k values, we can determine what are called key features for a quadratic function that's in this form. To find the key features, we use the a, the h, and the k, like I said. We'll start with that vertex. The vertex is that turning point for that function. Normally it's at 0, 0. But when we have a transformation, we know we move it left or right, and then up or down. And remember, anything with the x on the inside, we always do the opposite sign. But anything that's on the outside, we do the same sign for k. And we plot that point. The axis of symmetry is the equation of a vertical line. So it needs to be in this form, x equals h. And it's pretty easy to figure that out because h is the same coordinate as the x value for the vertex. And then you draw that vertical line. The y-intercept is the one where we have to show some work. We have to actually plug in 0 for x and simplify. And that would be the ordered pair 0, comma, whatever number you get when you simplify. And we would graph that point. Let's put this to the test for our equation at the right. It says state the key features for the quadratic function f of x equals 2 times x minus 3 squared plus 4. Then graph. We know our a, our h, and our k values from looking at that equation. Let's start with the vertex. Describing the transformation helps us determine the vertex. If it's x minus 3 on the inside, that means we go right 3. And the x-coordinate of the vertex would go right accordingly. So it starts with 3. Whatever's on the outside is how far up or down we go. So, when we described it, sorry about that, we'd say up 4. So then the vertex would be 4 for the y-coordinate. The second thing we'll do is we'll sketch the graph for the axis of symmetry. Remember, it's the equation of a line. So we always start it off as x equals. And we'll pick a different color. We'll go with orange. The nice thing about the axis of symmetry is it's always the x-coordinate of the vertex. Pretty easy point to get there. All right, so let's go ahead and graph our vertex. Well, let's wait till we're done. Sorry, we'll wait till we're done. This is exciting. Our y-intercept, the last thing that we'll calculate today. If we plug in 0 for x, we would get y equals 2 times 0 minus 3 squared plus 4. And now we have to simplify. Order of operations would have us do the inside first. Negative 3 squared would be positive 9. 2 times 9 is 18. And 18 plus 4 is 22. Yikes, that's kind of big. So that would be the point 0, comma 22. I'm not sure that's going to fit on our graph, so we'll have to come up with an alternate plan. Let's see what we have, though, so far. 3, 4 is our vertex. Let's go ahead and plot that point. The axis of symmetry is that dotted vertical line at x equals 3. So draw that in, if you would please, with arrows on the top and bottom. And then we're supposed to graph this y-intercept, but that's too far away. That's too far up on the y-axis. If that happens, we have to go back to making a table. We won't have to plug in too many points, and if we think about our symmetry, we should be in good shape for plotting additional points. Here's what I mean. We know that the vertex is 3, 4. If we pick another point close to the x value, like 4, let's see what happens. Plugging in 4 for x, we would have x minus 3, so 4 minus 3. 4 minus 3 is 1. We square that, 1 squared stays 1. Multiply that by the 2 out in front, we'd get 6. And if we add, multiply the 2 out in front, we'd get 2. And then if we add 4, we'd get 6. So 4, 6 should be a point on the graph. If I go over 4 and up 6, I'm just going to reflect that to the other side. Those 2 points should be both on the graph for that parabola. I'm just going to make that point hopefully a little bit closer to that number. There we go. Whoa. I don't know where that line came from. We're not ready to graph it yet. All right, we'll go with that. Sorry. All right, let's pick another number. How about 5? We'll just keep going. 5 minus 3 is 2, and then square that. 2 squared is 4. 4 times 2 would be 8, and 8 plus 4 would be 12. So that even goes off our graph a little bit, but I think that's a little bit easier to graph. So if we go over 5, we'll go up 12, so kind of up here a little bit. Reflect that to the other side, maybe close to here. I don't know, make that dot bigger. And you can kind of see the shape of that curve or that quadratic function starting to happen. Go ahead and draw a curve through your points with arrows towards the top. Now that we have our parabola on the shape of the graph, for the shape of the graph, let's finish up by stating the domain and the range. Domain and range, when you're looking at a graph, represent inputs and outputs. We also talked about this back in topic 1. For the domain, we look at the graph on the x-axis from left to right. And even though both of those arrows are technically pointing up, they're still kind of going to the left and the right. We can pretty much pick any numbers we want to plug in for x. That would mean our domain can go from negative infinity to positive infinity. The range, those are the output values, and we look at the bottom of the graph to the top of the graph. Now this time we have a boundary. At the bottom of the graph, our graph doesn't go any lower than the vertex when y equals 4. That would be the start of our range values. And since those arrows point up, that goes towards positive infinity. So there's just kind of a kickoff to sketching quadratic functions, starting with this form, the vertex form.